faster, quicker. Of all man's technical achievements, speed has been the longest obsession. On land, on water, in the air. Competition racing, breaking records, pushing limits.
It actually generates more power than a whole grid of 22 Grand Prix racing cars on the starting grid.
Nature's speed merchants use their pace to stay on top of the food chain. Technology's speed merchants have different priorities. In every domain, the race is on to claim the title as the fastest. Wild Tech explores speed. The world's most advanced fighter planes are required to perform aerobatics at breakneck speed. Evasive, fast, elusive. Nature's fighter aircraft have equally impressive skills. The Dragonfly devotes 24% of its body weight to wing muscle, allowing it to maneuver in all directions. The modern jet also devotes a significant proportion of its weight to its strong engines, capable of accelerating it to well beyond the speed of sound. Relatively, a Dragonfly's top speed of 30 miles per hour equates to a jet traveling at thousands of miles per hour. Its turns and acceleration expose it to pressures of over 30 G-forces. The one hindrance to jets performing like a Dragonfly is the human factor.
It makes no sense to build a wonderful combat aircraft if the pilot is the weakest point of the chain.
When a jet fighter pulls a simple slow turn at speed, centrifugal force can easily exert 9 Gs on his body. A 200-pound pilot now weighs 1,800 pounds. Gravity drives blood away from the brain, the heart, and the lungs towards the legs. Blood pressure decreasing rapidly around the eyes is the first sign of trouble.
The view range goes to a tunnel vision. First step. Second step is you are losing the colors. Next stage is blackout. Your eyes are open. You feel everything, you hear everything, but you have no view. And this is the last stage to recover by yourself. Then the next stage is the loss of consciousness, the G-lock.
Once in G-lock, a pilot could be unconscious for 20 to 30 seconds, traveling at beyond the speed of sound.
It means it's enough time to crash.
Former Swiss Air Force fighter pilot Andreas Reinhardt turned to nature's aerobatic genius, the Dragonfly, when he began to search for a solution to combat G-lock. On a comparable scale, its maneuvers would kill a fighter pilot. Nature's secret to withstanding this stress is to protect and stabilize the body's vital organs with a liquid cushion. At high Gs, the fluid absorbs the G-forces, enabling the cardiac system and the brain to function.
Sharon, ready to go to baseline?
Ready.
Here we go. We got 5.5 Gs loaded for you for 30 seconds.
Okay.
Currently, G-force protection for pilots relies on a cumbersome pneumatic anti-gravity suit. This protects by filling with compressed air and squeezing the body's lower extremities, pushing blood back toward the vital organs. Most G-suits take 2 seconds to respond to rapid force, critical moments which leave the pilot completely unprotected and prone to exhaustion. Andreas began experimenting with liquid-filled suits, reasoning the Dragonfly's simple protection may work on fighter pilots. He called his suit the Libelle, German for dragonfly.
This sample here shows our first G-suit, built 1988, filled with 28 liters of liquid. It works, a big sign into the right direction, bad and practical. Next one, called Flash Gordon. My personal favorite here. Looks good, great, was effective, but too complicated to make for the series, for the production. Next one, this is the current version for the market.
When subjected to G-forces, the suit's built-in liquid columns compress, squeezing the pilot, absorbing the G-force, and protecting the blood flow and organ function, quicker and more effectively than the pneumatic system.
It's the most effective, very simple working system, standalone, and it helps to really use the whole potential of the new generation of aircraft.
The quicker response of the Libelle liquid suit allows pilots to withstand stronger Gs and be less exhausted by the process, as shown in this test. On the left, vision of a pilot in a Libelle G-suit. On the right, the same pilot subjected to the same force in a conventional pneumatic suit. In the conventional suit, at 9 Gs, his breathing is labored. Stress hormones begin to flood his body, and his eyes begin to roll. But in the Libelle G-suit, he is able to talk and wave freely, even at 9 Gs.
Normal breathing. Lift the hand. Very slight gray out.
Other tests have been equally successful. This pilot is experiencing 10 Gs and comes through unscathed. Already, the German Air Force is certifying the Libelle for fighter pilots. And in the United States, it's anticipated the Navy and the Air Force will certify the G-suit within 3 years. Drawing from wildlife, this technology enables humans to withstand the pressures of high-speed travel. The next generation of high-speed travel also draws from wildlife, creating engines which will revolutionize the space industry. Flying fast. For the peregrine falcon, it's a technique that's made it nature's perfect hunting machine. With wings swept back like delta wing fighter aircraft, it dives at close to 200 miles per hour, the fastest animal on Earth. For mankind, the need for speed has created huge and powerful rockets, which can break the shackles of gravity. The key to being the fastest for both nature and technology is not just sleek design. It's an ability to consume a constant supply of oxygen in their engines. Birds never run out of air. Unlike human lungs, which breathe in and out, bird lungs work on a one-way flow-through system of air, augmented by sacs which pump air continually into the lungs. The peregrine travels so fast, the air is forced into its lungs at a rate other birds could not cope with. Baffles on the peregrine nostrils actually restrict airflow, allowing it to breathe at its maximum dive velocity. The notion of flying into air, forcing oxygen into the lungs, has given rocket scientists an idea which could revolutionize the space industry.
A scramjet takes oxygen out of the air by just flying along, just like a normal jet engine does, and it just gets rammed in the front of the engine.
Professor Alan Paul and his team from Queensland University, Australia, are pioneering a new era of rocket science, the supercombustion hypersonic scramjet.
We want a scramjet because there's two reasons. Is one, we'd like to fly faster. Mankind wants to fly faster, but secondly, we really want to get into space and make it a lot cheaper to get into space. And rockets just aren't going to do it for us. We've reached the limit of that technology, and we need a new technology to go into space and make it cheaper.
Current technology requires space vehicles to carry heavy payloads of oxygen and hydrogen to fuel the rocket engines to generate gravity-defying speed. The two large external rockets detach after boost and are recovered for future missions. The large central fuel tank is expensively discarded once it's done its job. Jets, on the other hand, do not require stored oxygen, sucking continuous air in, like the peregrine falcon. But their speed is significantly slower than rockets. The world's fastest air-breathing aircraft, the SR-71, cruises slightly above Mach 3. The highest speed attained by NASA's rocket-powered X-15 was Mach 6.7. A scramjet promises speeds of Mach 10, with the added bonus of reduced fuel load, cutting weight, cutting cost, and creating a totally reusable space vehicle.
A scramjet's just simply an engine like a normal jet engine. The difference is that a scramjet travels around about 8,000 kilometers an hour and upwards, whereas a normal jet engine travels about 1/10 of that speed. And they're really simple devices. This is a simple scramjet here. It consists of just an intake, a combustion chamber, and a thrust surface. The intake, all it is like the piston in your car. It just compresses the air from here down into there. And this is a diesel. There's no spark plug, so the temperature's high enough for it to burn. And this takes this long to burn. And then once the fuel burns, it's released, the energy is released on the back and pushes along. Testing of a scramjet is actually a pretty hard business because you've really got to get it up to these speeds to start with. And so you're really going through an area of flight which is untested anyway, except for things like space shuttles and so forth. So it's really hard and really difficult and really expensive.
Before assessing its performance in flight, the prototype, called High Shot, is tested inside this shock tunnel, where a heavy metal piston fires down a barrel.
You can compare this to a big bike pump, and pretty fast one with a pretty big piston in it, but all it is just getting a big bike pump and compressing the air in front of it, and then at some point at time, when it gets up high enough pressure, it lets go and lets all that air out. We load up a big piston, and that piston is then fired in that direction down there, and compressors in front of it, usually helium or argon or some inert gas like that. It pushes this gas up against a diaphragm, which is just a piece of sheet metal. The piston comes down from up that end there and builds up pressure in front of it and builds up to a point where it actually bursts the diaphragm and puts a hole in it like that, just like the balloon bursts. When the diaphragm bursts up there, it creates what we call a shock wave, and that shock wave comes down this tube, and when we're in reflected mode, it reflects off this point here and goes back and creates this really high pressure, high temperature region here. And then we expand it out of a nozzle, and that nozzle would normally fit in over here into the test section where we place our scramjet. And then the air just flows over the model, and we would take our measurements in the 1 or 2 milliseconds of test time that we have.
The only experiment which has proved scramjet theory took place in this test tunnel, and then for only a fraction of a second. The tunnel created gas speeds of between Mach 8 and Mach 15, the type of speeds necessary to create a scramjet. It took a decade of preparation and failed tests before scientists were ready to launch a vehicle which could fly under scramjet power. In July 2002, Highshot was prepared for takeoff in the remote desert of Central Australia.
What you see here is just before launch. As we take off, we've got about Mach 1 now, and you'll be going up there and you've got 6 seconds for the first stage to burn, and then it's burn out just there. And then we coast for 11 seconds until the second stage burns, and it seems to come in at a funny angle, but then you see it'll take off, and there it goes there. It takes off a nice straight burn. You can see the plume is nice and straight, a little bit of wiggles, but that's what you see from the wind anyway. And basically at this point in time we knew that we were on track, we knew everything was going right. That rocket continues to burn for about another 30 seconds and gets it to the outside of the atmosphere. And then it just is going so fast that it lobs it up in the air, and we have to wait 10 minutes before it comes back again. And that's when we do all the tests. We actually had to go to an altitude of 315 kilometres, and just to give you an idea, that's sort of where the space station hangs around, and then let it fall back down to the ground, and it was on the way back down to the ground that we did the experiment, and we had our 5 seconds of joy.
As the rocket falls at supersonic speed, air is forced into the scramjet and mixed with hydrogen from the tank. The speed and compression of the atmospheric air intake causes the fuel mix temperature to rise quickly and self-ignite, propelling the scramjet to speeds of Mach 8 and greater. A light recorder is ejected before the rocket crashes, allowing the scientists to study the data.
The data's looking very good, and it's really what we can claim is the first time supersonic combustion, which is inherent to a scramjet, has been undertaken in flight. When you look at that thing flying at Mach 8, and we've got pictures of it, it just blows your mind away. You know, how the hell can that actually work like that? And it does it exactly the way you expect it to do it. So yeah, it's pretty exciting.
Scramjet technology is also being developed by NASA. The HyperX program plans to use a conventional aircraft to launch a Pegasus boost rocket to lift it 100,000 feet. At this height, the scramjet is traveling fast enough for air to be rammed at high pressure into its hydrogen combustion chamber, generating the force to deliver speeds of 2 miles per second, 7,200 miles per hour. Eventually, The promise of the technology is cheaper space launches with greater payloads. Pushing speed, pushing limits. Nature's speedsters have also taught mankind no domain is a slow speed zone, even underwater. Science fiction animators have recognized there is one frontier still to be tested for extreme speed: underwater. They've envisaged jet-engined underwater vehicles that can travel in a pocket of air, eliminating drag. In fact, their underwater speed machines are closer to reality than ever before. One of the fastest underwater creatures is the marlin. Its streamlined body and strong tail capable of pushing it to 50 miles per hour. The fastest man can travel underwater at present is by submarine at 40 miles per hour, though torpedoes can travel faster. Clearly, cutting through water is no easy business, with good reason. Water is nearly 800 times denser than air. It follows that the higher the density of a medium, the more effort it takes to push through it. Add to that the salinity, temperature, and pressure at depth, and these speeds don't seem quite so pedestrian. It puts the great white shark's relatively slow speed of 22 miles per hour into perspective. Its underwater acceleration against the force of water makes it an impressive predator. Water is also around 55 times more resistant to flow than air. A layer of fluid sticks to the surface of any body moving through water. As speed and the object's size increases, so does drag. The fastest fish have evolved to tackle the drag problem in different ways. Marlin have streamlined shapes, overcoming much water pressure drag. Dolphins and whales adjust their skin tension, also reducing drag. Humans have copied these ideas for decades in marine technology, but scientists have now hit upon an idea which nature cannot replicate: reducing drag completely. They call it supercavitation.
Normally when a vehicle is traveling through a fluid, it's affected by a very high drag through the action of the water moving across the surface of the body. And the way to reduce that drag is to create a bubble around the vehicle to eliminate the friction forces on the body. And supercavitation is a way to create that bubble.
Tom Giesecke from the Naval Undersea Water Center is developing torpedoes and underwater bullets. And, most remarkably, they create a cushion of air which eliminates drag and allows tremendous speed.
At very high speeds of the order of 100 to 200 knots, a cavitation bubble will form at the front of a vehicle moving through the water. If the vehicle is designed properly, or the vehicle is moving fast enough, that bubble can envelop the entire vehicle, and the skin friction is eliminated, and the vehicle can go at high speeds.
Well, I guess you'd have to do the calculation, but it would probably be way up inside there.
Yeah.
In order to keep the center.
And I don't know how far up.
Giesecke and his team are exploiting a natural phenomenon that has been known for some time: cavitation, where water vapor bubbles form around objects moving through water. On a propeller, cavitation can cause a lack of drive when the blades effectively lose contact with the water. When cavitation occurs at the front of a streamlined vehicle, like a torpedo or bullet, the water vapor envelops the vehicle, creating a supercavity that eliminates water drag. Nature's underwater speedsters could not achieve the velocity required to form a supercavity. Technology has left nature in its wake.
Well, there's a bunch of differences between bullets and torpedoes. Well, first obvious difference is the size. The second is the speed. Bullets travel much faster, pushing the speed of sound in water, which is 1,500 meters per second, whereas torpedoes travel at much lower speeds, more like 100 meters per second, which is about 200 knots, in their operation. One of the other key differences, because they're traveling at different speeds, they have different means of creating the bubble that envelops, the supercavity that envelops the vehicle. For the bullet, it's going fast enough that water vapor actually is created at the tip of the bullet and envelops the entire projectile, and therefore you get the drag reduction. On the torpedo, since it's going much slower, a natural cavity would only cover maybe the first foot or so, depending on the speed of the torpedo. So what we do to compensate for that is inject air to allow the bullet, or the gas, to envelop the entire torpedo. We have a number of models that we use to look at different elements of the vehicle and the subcomponents and how they work together. Kind of important issues in particular is how the cavity forms, how the cavitator, or the disc at the front of the vehicle, generates the bubble, what sort of ventilation rates are required to sustain the bubble under different conditions, and then what happens to the cavity when it interacts with different parts of the vehicle.
Creating torpedoes and bullets which can travel at the speed of sound requires exacting physics, and the pressure is on. It's rumored the Russian Navy already has supercavitating torpedoes.
This is a mock-up of what we see as the first generation of the undersea torpedo, or supercavitating torpedo. It's propelled by a conventional propulsion system, a solid rocket motor, with a thrust vectoring system on the back end. And at the other end is really the most important part of the supercavitating vehicle, which is the cavitator. And the cavitator creates the bubble through which the vehicle travels. The other major weapon system that we're working on is the undersea bullets, and this is a project that I spend most of my time working with. This is considerably different than the torpedo system in that it's a much higher speed weapon system. These bullets go nearly the speed of sound in water, which allows them to create their own cavity and travel the range from the weapon system to the target almost instantly. So really what you end up with when a bullet is flying through the water is an enormous long cavity with a tiny little bullet at the front end of it. And part of the design process, or the design challenge, is how to get the most bullet you can inside that cavity.
The speed and pressures on the underwater projectiles make for dramatic failures.
This is what happens when a bullet fails in flight. This never actually struck anything in water, but it was going so fast and the forces were so severe that it caused it to roll up and go through this failure mode. And you have to remember that when you're going through water, the density is orders of magnitude higher than it is in air. So the forces similarly are just through the roof. And this is what can happen if things aren't designed properly.
Scientists agree there's a long way before the technology will include the submarine, but it's not impossible.
As it stands now, there's no requirement for ships that go at 100 knots, 200 knots. But there's no technical reason why you couldn't build something like that if you had the right propulsion system and the right ventilation system and the right engineering that went behind it.
Supercavitating systems could bring about a quantum leap in undersea naval maneuvers. the need for speed being a driving force in military application. It's a basic strategy that has implications across the armed forces, even down to individual soldiers. The soldier. For insects and for man, they are the backbone of any conflict. But it's the ant's exoskeleton which, size for size, gives it the edge over the most battle-hardened marine. Applying ant speed to humans would mean we could move at hundreds of miles an hour. Not only that, the ant can lift 20 times its own body weight. Imagine if human soldiers could be as relatively fast and strong as the ant.
If I need to carry 2 of my buddies out of combat, completely combat loaded, and get them to a safe area, and they're both weighing in excess of 200 pounds apiece, the exoskeleton will go to work for me instantly, noticing that I'm carrying more weight. It'll instantly make it feel like I'm only carrying 15% of my weight. In all actuality, I'm carrying, 400 or 500 pounds.
The U.S. Army's Natick Soldier Center is working on a suit they call the Future Warrior. Their concept is a stronger soldier is a faster soldier. More speed, more efficiency, and safer.
Well, the military expects a soldier under full load to move about 2 kilometers per hour, which doesn't sound very fast until you think about the fact that their backpack weighs about 80 pounds. And they have about another 40 pounds of helmet and flak jackets and all sorts of things that they have to bring along with them. How can we move these soldiers more quickly under load? How can we take a human being with limited endurance and have them move under load at sort of, speeds of maybe 6 or 8 kilometers an hour?
Cornell University's Ephraim Garcia is working on an exoskeleton concept to enhance soldier speed. They will travel faster, for longer, require less brakes, and tire less easily. A soldier's race is the marathon, not the sprint. They need to be non-stop running machines, as physically able as the ant.
Yeah, exoskeletons are not exactly new. They sort of have been in the human psyche. This idea of melding man and machine has been with us for a long, long time.
The problem for scientists is finding a suitable power source for an exoskeleton. Garcia and his team research new technologies by having fun with their robotic test unit, the BattleBot.
The similarities between the BattleBot and the exoskeleton really will come in the fact that in both cases the machine is energetically autonomous. That is, it has to carry its power on board. Controls have to be part of the mechanism itself, so the machine has to carry its own controllers, its own power. It has to distribute that power in a rational way to its actuation system. Can we create an exoskeleton that has sensors, can respond to human motions, and deliver power to a series of actuators to allow sort of fluid human motion inside of this machine? Speed, strength, and endurance can be augmented with an exoskeleton. So the challenge for us as engineers is to try and figure out how can we take high energy dense fuel like gasoline or some hydrocarbon fuel or diesel and take all the energy in that fuel and somehow convert that to maybe hydraulic actuators, and somehow convert the information of motion in the body to command signals in the computer that will tell those hydraulic actuators how to move. So it's this creature that we're creating, in some sense, this wearable robotic system that would go over a human being.
It's hard to believe that the toy robots of this research institute could become the basis of the power suit for the battle-hardened soldier.
The goal right now, and the goal of the program that I started at DARPA, is really to just see if it's feasible. You know, has the technology in biomechanics, controls and electronics, actuation systems and miniaturizing actuation systems and materials, has all of that sort of coalesced to the point to actually make exoskeletons possible? Is it feasible to be doing this? I think it is.
The military applications for faster soldiers, faster machines, or faster jets is driven by tactical and economic requirements to do a better job, cheaper and quicker. But human nature is about more than that. The drive to be quick on land or in water stems from a competitive edge which compels some people to be simply known as the fastest on Earth. Nature's land speed freak, the cheetah, can sprint at 60 miles an hour. The fastest unaided man on Earth runs at around 27 miles per hour. The cheetah uses its speed to cut down gazelle in full flight. It's the animal's desire for survival, not its desire for records, which drive the cheetah's need for speed. Man's drive to go faster also grew from survival. Catching prey required strength and agility. More prey meant more food for your tribe. It was survival of the fastest. The desire to be fast became entrenched in the human psyche. Now, technology has allowed the human spirit for speed to be transferred to super machines, which take us to speeds where nature cannot travel. Legends like Sir Donald Campbell and his Bluebird attempts on both land and water speed records captured the imagination of a world craving the promises of fast, jet-powered technology. In the 21st century, that craving to be named the fastest man on Earth still drives the speed merchants.
My name is Ed Shadle. I'm the co-owner, builder, and driver of the North American Eagle World Land Speed Record Challenger.
Speed on land.
The engine in this is such a big, powerful engine. I mean, the engine weighs over a ton.
Speed on water. Two men, two ambitions, pursuing records that have driven man's imagination since the invention of the wheel.
The day Andy Green broke the record was an awesome day and certainly moved land speed racing forward many, many years. The power, the speed was just beyond what you would ever imagine.
This may look like an aircraft, and in fact once was, but it has been reincarnated as the vehicle Ed Shadle hopes will propel him to the title of the fastest man on land.
This aircraft has been reborn. It came from the junkyard, so to speak. It was about 6 weeks away from being a Foster's can. And when my partner Keith and I brought this thing home and we started scraping paint off of it, and there were about 15 layers of paint, and we found its aircraft number was 763, which seems kind of strange because the record is 763. And we found this information out as we've been working on it, and we found that this thing had a unique history. And so that really kind of gives the whole team a feeling of camaraderie around this aircraft. I mean, it's a special airplane. And we didn't know it at the time, but the more we work on it, the more we've discovered this. The aircraft itself, I think, just has such a unique history that's worth its weight in gold just on its own. We've used the entire F-104 fuselage, minus the wings and the horizontal stabilizer. We've had to shorten the tail by a little bit. We cut about 10 inches off the vertical. Otherwise, it's very much the same. We're using an F-104 engine, the J79, and otherwise it's pretty much the same. We have a lot of modifications that we've done, but the basic core is still an F-104.
In a plane, the J79 engine has hit 1,200 miles per hour. When ready for its assault on the land speed record, the vehicle will take 3 miles to build to a top speed of an estimated 800 miles per hour. Nose lift will be the vehicle's main problem, given it was originally designed to fly. To compensate, the designers have added forward computer-controlled canards, which will react and tilt if nose lift is sensed, putting downward thrust on the vehicle.
It's daring, it's exciting, but if you do it in a controlled environment, you get the thrill of all those things without killing yourself or, Everyone asks me if the ejection seat is armed. My answer to them is if I'm right side up, I don't need to eject. If I'm upside down, I don't want to eject.
Jet technology will also power the attempt on the world water speed record in a boat named Quicksilver.
The advent of the jet engine was a big impact, obviously, on the aviation world, first of all, but it was very rapidly adapted and adopted by the community for speed records on water, because you get rid of all the problems of having a propeller, a gearbox, a drive shaft. You lose efficiency through all of those media. This is something that will just allow all the energy of the jet to be translated into forward energy straight away.
Even nature has recognized the acceleration advantages of the jet in a surprising creature. The squid compresses water and forces it out. The laws of physics dictate this action as an equal and opposite reaction, and the squid shoots away. The same laws apply to Quicksilver with its massive jet engine.
There's an analogy with the squid in that jet propulsion is used, so it's the expulsion of air as opposed to water with the squid.
Unlike the squid, Quicksilver travels on the water, not under it. Aerodynamics will be the key factor for speed and safety.
Donald Campbell's fatal crash was a national event, but it's something that's actually permeated the British consciousness. And we've taken the Bluebird concept and actually turned it back to front. We have these floats, what are called sponsons, at the back, where they create less disturbance in the airflow than having them at the front. The boat weighs 7,000 pounds, but it has 11,000 pounds of thrust, so it actually has a lot more power than it has weight, so it should be a really very hot performing machine.
Extensive testing in water tanks is crucial, if the team hopes to break the world water speed record of 317.6 miles per hour.
It's basically getting the center of gravity just right, and also
you know, get the information that you need from down from those drawings, and then we can balance it.
By simulating airflow mathematically, then testing in a wind tunnel, Quicksilver's drag can be minimized.
We worked on the design of this very extensively in the wind tunnel to try to optimize the shape of the pattern of the air as it moves through over the shape of the boat to the engine. We've reached the point now with the boat where it's starting to come to life. The systems are starting to work. Okay, now you can hear the revs building up as I've started the engine, and the revs are climbing, and my exhaust gas temperature here is going up as well. And you can hear as the revs go up, the software is doing tests of itself to make sure the engine is running correctly throughout this startup procedure. Now, if I ran this big engine behind me, it would blow the whole building down, so it's impractical. We have this connected to a small jet engine, a miniature one, that we have just pushed outside the doors. And that's what we're operating, but we're doing that from the cockpit of Quicksilver. The real engine in the boat is actually 100 times more powerful than this one you hear behind me.
When Quicksilver is finished its exhaustive testing, the hope is it will hit speeds above 320 miles an hour. There will be no room for error.
Certainly, I love life and I want to live. I want to come through this and be able to enjoy the fact that I am the holder of the record. And if we weren't bothered about the risk, we wouldn't be taking so many efforts with trying to make sure the boat's designed properly and the safety measures. But it's really the human element. It's a human being in there, being in the loop and being at risk that's actually part of it. And there's an important distinction between that and having a death wish, though.
Nature's supreme speedsters, the cheetahs, the falcon, the marlin. They sit at the top of the food chain. For man, take technology out of the equation, and we are left on the starting block. It is our yearning to go faster which has driven us out of the natural speed contest and into an unmatched race. It's a drive that never ends, on land, on water, even underwater. Technology takes the human speedster into an extreme world where life in the slow lane is not an option.